Welcome to a grand voyage across the cosmos, where our planet Earth is just one among an estimated 100 billion worlds. These planets dance around some 400 billion stars, which together weave the vast tapestry of our Milky Way galaxy, a spectacular spiral of celestial artistry. Imagine the galaxies as cosmic canvases, with stars as their brilliant brushstrokes and planets as the intricate details that bring the universe to life. Our very existence and the story of our solar system are deeply intertwined with these galactic tales. The epic of the Milky Way unfolds nearly 13.6 billion years ago, a mere heartbeat after the universe's explosive birth in the Big Bang. Back then, there were no stars, no planets, only a roiling, superheated fog of hydrogen gas. As millennia passed, this cosmic mist cooled, and gravity began its relentless work, sculpting the gas into denser clumps. These clumps grew heavier and hotter until, finally, hydrogen atoms fused to form the first stars. These blazing suns ignited across the galaxy, heralding the dawn of the Milky Way. Think of a galaxy as a living entity, not so unlike ourselves. In its youth, it's dynamic and effervescent, zealously forming stars and growing in fits and starts, much like a teenager in the throes of adolescence. And as it ages, it settles into a more measured pace, akin to the steady stride of middle age. What truly defines a galaxy? Over time, each galaxy establishes its own unique structure. But like everything in the cosmos, it too will eventually cease to form stars. And just like us, it will meet its end. So, where does our Milky Way stand in this cosmic life cycle? Is it a vibrant, youthful galaxy, or is it nearing its twilight? Scientists have a fascinating method to determine a galaxy's age and vitality through its color. Across the universe, galaxies don a spectrum of colors that tell a story of their past. Young, spirited galaxies radiate a brilliant blue, their color reflecting the intense light of hot, newly born stars. On the other hand, older, quieter galaxies glow with a mellow red, their color marking a time of fading light and ceased star formation. These mature galaxies are filled with older, cooler stars, casting a subdued hue across their vast expanses. So, what color is the Milky Way? This question might seem simple, yet it's incredibly complex to answer. Despite observing the Milky Way for millennia, pinning down its exact stage of life remains elusive. The name Milky Way itself harks back to ancient times when people gazed up at the night sky and saw a mysterious band of light arcing across the heavens. Embark on this celestial journey as we delve deeper into the life story of our galaxy, exploring the vibrant youth and quiet senescence of the cosmos. Through the colors of the universe, we unlock the age-old secrets of galaxies far and wide, including our own Milky Way. Imagine looking up at the night sky and seeing a band of light stretching from horizon to horizon. This mesmerizing strip, which turned out to be composed of countless stars, was once too distant for our ancestors to discern as individual points of light. It took centuries for us to grasp the true shape and vast scale of our home galaxy, the Milky Way. The astonishing reality is that we are still piecing together the mysteries of the Milky Way. Nestled within a disk of gas and dust, our position obscures our view of the galaxy's heart and its farthest reaches when we rely on visible light alone. To truly unlock the secrets of the Milky Way, scientists turn to infrared light, which can pierce through the cosmic fog. Deep in the heart of New Mexico, the Sloan Digital Sky Survey Telescope at the Apache Point Observatory is doing just that. By mapping the galaxy in infrared, this remarkable instrument offers scientists a clearer view and deeper understanding than ever before. Remarkably, it's only within the last 15 years that we've begun to harness the power of sensitive infrared observations to explore our galaxy in this way. Each new observation with technologies like Sloan opens a fresh window onto the universe, teaching us more not just about our celestial neighborhood, but also about the very fabric of space itself. As we continue to explore, the last 15 years have revolutionized our understanding of the Milky Way, revealing its hidden structures and vibrant life cycle in unprecedented detail. The Sloan Digital Sky Survey has embarked on an astronomical mission, scanning the heavens to analyze over 250 million stars. Their goal? To unravel the true color of the Milky Way. What they discovered, however, has sent shockwaves through the scientific community. For years, we pictured the Milky Way as a vibrant, youthful galaxy. But recent findings suggest a startling twist in our galaxy's story. It may be on a slow decline toward demise. The Sloan telescope has revealed a drastic drop in star production within our galaxy. It's a grim prognosis. The Milky Way is dying, despite having abundant reserves of star-forming gas, enough to suggest a flourishing galactic environment. The rate of new star formation is plummeting. It's as if the Milky Way, rich with hydrogen gas and dense dust clouds, has all the necessary ingredients for stellar creation, yet is inexplicably fading away. Now, with a potential galaxy killer at large, scientists are launching what could be described as the most colossal murder mystery investigation in cosmic history. They're probing this perplexing slowdown, trying to pinpoint what's stifling the life out of our galaxy. This quest is not just about understanding the fate of the Milky Way. It's a journey to grasp the underlying forces that govern the life cycle of galaxies across the universe. Imagine you're a detective at a cosmic crime scene, with the universe itself laying out clues in a silent, star-studded expanse. Our target? Not Earth, but our very home in the cosmos, the Milky Way galaxy, which, after billions of years as a prolific star factory, is showing signs of imminent shutdown. The tale of star birth within the Milky Way is a storied one. Our own sun, a relatively young star, ignited about 4.5 billion years ago, but it's far from the oldest in our galaxy. Alarmingly, it appears to be among the last in a dwindling generation. Current estimates suggest that in just 4 billion years, a mere moment on the cosmic clock star formation might grind to a halt. To unravel this mystery, scientists have launched a forensic investigation of galactic proportions. The pressing question: how is the Milky Way dying? The lifeblood of new stars, cold gas, must be preserved for a galaxy to thrive. To snuff out a galaxy, one would have to expel this gas, drain it away, heat it past its prime, deplete it entirely, or disrupt its flow through countless other cosmic means. As this investigation unfolds, researchers are piecing together the mechanisms that could lead to our galaxy's quiet demise. Each discovery brings us closer to understanding not just the future of the Milky Way, but the life cycles of galaxies across the universe. Our mission is to pinpoint exactly what is bringing about the slow demise of our galaxy. Could the cause be lurking within the Milky Way itself? In search of answers, we look beyond our cosmic neighborhood to a distant galaxy known as W2246526, affectionately nicknamed a hot DOG hot dust, obscured galaxy by astronomers. Situated a staggering 12.2 billion light-years away, W2246526 holds the title of the brightest galaxy known in the universe, radiating with the light equivalent of 300 trillion stars. However, the true source of this blinding brilliance isn't its stars. Instead, it centers around a much smaller, yet incredibly powerful phenomenon at the heart of the galaxy, a supermassive black hole, about 1 million times smaller than the galaxy itself. This revelation offers a compelling clue. Could a similar cosmic titan be the hidden force driving the Milky Way towards its quiet end? As we explore this possibility, we delve deeper into the cosmic mysteries that govern not only the life and death of stars, but of entire galaxies. The Milky Way, a name that stirs the imagination, is the galaxy that contains our solar system. But how old is this sprawling mass of stars and cosmic dust? Scientists estimate that the Milky Way is about 6 billion years old, nearly as ancient as the universe itself. This age is determined through the study of the oldest stars and the chemical composition of the galaxy. To understand the age of the Milky Way, we need to look at the life cycle of its stars. Our galaxy is filled with stars at various stages of their life cycle, from young blue stars to ancient red dwarfs. By studying these stars, astronomers can trace back to the early days of the galaxy. The oldest known stars provide clues about the galaxy's formation and its early history. How did the Milky Way form? The leading theory suggests that the galaxy was formed from a large cloud of gas and dust, which collapsed under its own gravitational pull. This process triggered the formation of stars and led to the spinning disc-shaped structure we observe today. Further studies of globular clusters and the motion of galaxies help refine our understanding of this formation. Dark matter plays a crucial role in the formation and stability of the Milky Way. This mysterious substance, which does not emit light or energy, makes up about 85% of the total mass of the universe. The gravitational effects of dark matter help hold the galaxy together and influence its rotational speed and spiral structure. As technology advances, so does our understanding of the Milky Way. Missions like the Gaia spacecraft are mapping billions of stars, providing unprecedented detail about the galaxy's structure and dynamics. Future research promises to uncover more about the Milky Way's past, including how it has evolved over billions of years and how it will continue to change. One of the most significant ways astronomers estimate the age of our galaxy is by studying its oldest stars. Some of the oldest stars found in the Milky Way, known as population II stars, are nearly 13 billion years old. These stars lack the heavier elements that younger stars have, indicating they formed during the early days of the galaxy. Understanding these ancient stars gives us a glimpse into the galaxy's youth. The Milky Way's halo, a spherical region surrounding the galaxy, contains some of the oldest objects in the galaxy. This region is sparsely populated with stars, globular clusters, and dark matter. The halo's stars are typically older and have lower metallicity compared to stars in the galactic disk. Studying the halo helps us piece together the galaxy's early evolutionary stages. Globular clusters are dense groups of ancient stars that orbit the Milky Way's center. They contain some of the oldest stars in the galaxy, some dating back over 12 billion years. These clusters provide critical insights into the conditions present when the Milky Way was in its infancy. By studying them, we can learn more about how the galaxy was assembled over time. Supernovae, the explosive deaths of massive stars, play a crucial role in the galaxy's development. These powerful events disperse heavy elements into space, enriching future generations of stars. Over billions of years, this process has transformed the composition of the galaxy. Supernovae also impact star formation, triggering the collapse of gas clouds that eventually form new stars. The Milky Way is a barred spiral galaxy, with distinctive spiral arms filled with stars, gas, and dust. These arms are not static. They evolve over time as stars move and interact with each other. The age and composition of stars in the spiral arms tell us about the galaxy's history and how it has changed over billions of years. Understanding the arms' dynamics is key to unraveling the Milky Way's past. At the core of the Milky Way lies the central bulge, a densely packed region of old stars. The stars here are generally older than those in the disk, with many forming more than 10 billion years ago. This region's complex structure offers clues about the galaxy's early history and the processes that shaped it into the galaxy we see today. The supermassive black hole at the center of the Milky Way, known as Sagittarius AE, plays a pivotal role in the galaxy's evolution. Over billions of years, this black hole has influenced the motion of stars and the structure of the central bulge. Its immense gravity shapes the behavior of everything around it, making it a critical factor in understanding the galaxy's development. The Milky Way has both a thick disk and a thin disk, each with distinct characteristics. The thick disk contains older stars and has a different composition compared to the younger, more metal-rich thin disk. Studying the differences between these two disks helps scientists trace the galaxy's formation and the various mergers and interactions it has experienced over time. The Milky Way didn't form in isolation. It grew over time by merging with smaller galaxies, a process known as galactic cannibalism. Evidence of these mergers is found in the streams of stars and gas that still orbit the galaxy. Understanding these past interactions gives us a clearer picture of how the Milky Way grew to its current size and structure. While much of our focus has been on the past, the Milky Way's future is also fascinating. In about 4.5 billion years, our galaxy is expected to collide with the neighboring Andromeda galaxy. This colossal event will reshape both galaxies, creating a new, larger elliptical galaxy. While this may sound catastrophic, the vast distances between stars mean that our solar system may survive relatively unscathed. The Milky Way is part of a collection of galaxies known as the Local Group, which includes Andromeda and dozens of smaller galaxies. The interactions between these galaxies, including gravitational pulls and eventual mergers, have played a significant role in shaping the Milky Way's evolution. Studying the Local Group helps astronomers understand how galaxies influence each other over cosmic time. Cosmic rays, high-energy particles from outside the solar system, constantly bombard the Milky Way. These particles play a role in processes such as star formation and even the evolution of life on Earth. Understanding how cosmic rays interact with the galaxy provides another layer of insight into its complex and dynamic history. The rate of star formation in the Milky Way has varied dramatically over billions of years. During its early history, the galaxy underwent periods of rapid star formation, followed by more quiescent phases. By studying these fluctuations, astronomers can learn about the galaxy's interactions with other galaxies, gas inflows, and the internal processes that drive star formation. As stars evolve, they produce heavier elements through nuclear fusion, which are then spread throughout the galaxy by supernovae. Over billions of years, this process has enriched the Milky Way with elements like carbon, oxygen, and iron. By analyzing the chemical composition of stars, astronomers can trace the history of element production and gain insights into the processes that have shaped the galaxy. Mapping the Milky Way is no easy task, given that we are inside it. However, missions like Gaia are providing detailed maps of the galaxy's stars, revealing the structure and motion of billions of stars. These maps are crucial for understanding the galaxy's history, from its formation to its current state. They also help us predict how the Milky Way will evolve in the future. The Milky Way is surrounded by an enormous halo of dark matter that extends far beyond the visible galaxy. Though we can't directly see dark matter, its gravitational effects are evident in the way stars and gas move within the galaxy. This dark matter halo likely played a crucial role in the galaxy's formation, influencing its structure and dynamics from the very beginning. The Milky Way is not an isolated entity. It's part of a vast cosmic web of galaxies, connected by filaments of dark matter and gas. The way the Milky Way interacts with these large-scale structures has influenced its evolution over billions of years. Understanding these connections helps us see the galaxy as part of a much larger cosmic ecosystem. The Milky Way's central bar, a feature that distinguishes it as a barred spiral galaxy, is a relatively recent development in its history. This elongated structure of stars likely formed due to gravitational interactions within the galaxy. The bar plays a significant role in driving gas toward the galactic center, fueling star formation and influencing the motion of stars throughout the galaxy. The Milky Way is surrounded by several dwarf galaxies, such as the Large and Small Magellanic Clouds. These satellite galaxies are slowly being pulled apart by the Milky Way's gravity, contributing stars and gas to our galaxy. Studying these dwarf galaxies provides insights into the Milky Way's growth through accretion and its gravitational interactions with smaller neighbors. One of the puzzles in understanding the Milky Way is the missing satellites problem. Based on dark matter models, astronomers expected to find many more dwarf galaxies orbiting the Milky Way than have been observed. Solving this mystery could reveal important details about the nature of dark matter and the early history of the galaxy. The Milky Way's magnetic field, though much weaker than that of a typical fridge magnet, plays a significant role in shaping the galaxy. Magnetic fields influence the motion of gas, star formation, and even the structure of spiral arms. Understanding the role of magnetic fields adds another layer of complexity to our knowledge of the Milky Way's history and evolution. At the heart of the Milky Way lies its galactic center, a bustling region dominated by the supermassive black hole, Sagittarius A. This area is densely packed with stars, gas clouds, and intense radiation. The galactic center plays a crucial role in regulating star formation across the galaxy. Understanding the dynamic processes occurring here provides key insights into how the Milky Way evolved and continues to change. Stellar streams are trails of stars left behind by dwarf galaxies or star clusters that have been torn apart by the Milky Way's gravity. These streams are like cosmic fossils, providing evidence of past galactic mergers. By studying them, astronomers can reconstruct the Milky Way's growth history and better understand the interactions that shaped it over billions of years. One of the most significant observations made about the Milky Way is its flat rotation curve, where stars at the outer edges of the galaxy move at nearly the same speed as those closer to the center. This behavior is unexpected based on visible matter alone and is a key indicator of the presence of dark matter. Analyzing the rotation curve has allowed astronomers to map the distribution of dark matter throughout the galaxy. The Milky Way is a master at recycling. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.